Swayam Prabha. Digital India. Educated India.
Welcome back. In lecture 52, we will talk about IoT system architecture, and this is part 1 of the lecture. So, the different concepts that we will cover will be on computer process control system, then IoT architecture, core IoT technologies, IoT development platforms, and software ID. So, in the last lecture, we mentioned something about computer process control systems. So, that is the fundamental, the way or the legacy way how computers actually can control certain kinds of or sense certain kind of processes and then run and then control certain kind of processes as well. So, a computer process control system is where a computer monitors and controls a physical process, and then as per the output of that particular process, whatever is the feedback, this is used to actually improve the process further, and that's why it is also known as the closed loop control architecture. So, it's a process using feedback typically based on a closed loop control architecture, and that means output is continuously monitored and feedback loop to automatically correct deviations. Now, exactly how the deviations is corrected, so there must some logic has to be applied on based on the observed quantities and the desired quantities that we want. So, so this system has got several stages or several steps you can say, or several components you can say. So, the first is of course the sensors part, and the sensors measures the system state. That is, either it's a closed system we are measuring itself, or it could measure the environment as well. So, basically it is measuring a physical real world signal, and in most cases physical real world signals are analog in nature, right? And this same data is sent to embedded systems or computer systems. Embedded system means it is again, it could be a microcontroller or certain system which is embedded within a larger system, right? So, it could be a full computer system or a part of that. So, these systems are digital in nature. So, that means from analog we are converting to digital in most cases. So, who does this conversion? ADC does that. ADC is analog to digital converter, right? It converts analog signals to digital form, so a computer can process them. Otherwise, a computer will not be able to read that particular signal. So, the controller computes control action. That means once the signal is received by the controller or microcontroller, right, then it takes some action. What action? It depends on whatever code we have given to it. Based on that, it will take actions, or whatever algorithms we have uploaded to it. Accordingly, it will do some action. It could be PID, like the things which you need to do to run your own systems. It could be certain kinds of logic rules. That means if this is received, this has to be sent in a certain way. Or it could be some AI models based on the data that we are getting. It can do some predictions and then do something. So, all this would be used to generate some form of digital output coming out of this particular microcontroller. And this digital output is then converted by a DAC converter, a digital to analog converter, because most of the actuators are again will not be able to understand the digital signal. It will understand a analog signal. That means it is not just zeros and one. Some cases yes, in case it's a switch, there is only two positions, 0 to 1. But if there is a fan or if there is some motor and we want to control it, so in some cases we have to send an analog signal like change of voltage or something. So, DAC converts digital to analog physical control signals, that is analog voltage current that has to be done, and sometimes DAC is not required also when actuator is simple on off relay or something which can accept a digital signal. So, actuators are the ones which are connected devices to this system which are able to modify the process. That means modify the system to a certain extent. So, what are those actuators? It could be motors, it could be valves, it could be relays, it could be switches, and we will discuss this in detail later, who does what, and then this can be used to physically change the system. For example, if I want to increase the amount of airflow in a room, I will increase the fan speed, right? So that's increasing the speed can happen via IoT system, and I may be sitting, in a different room and can still control this. So usually this involves analog voltage, current signal, and sometimes a PWM pulse width modulation signal, which is like digital signal, but it acts as a analog signal. So we will learn about this in detail also in the subsequent lectures. So these are the key things that actually actuators requires to do something. So finally is the feedback, and the feedback that we get from the actuation process actually is used to stabilize the system further. So this is the computer process control system. But modern IoT architecture is different from this particular classical system, even though sometimes we assume that this classical computer process control system is nothing but IoT, and of course the data happens over internet, right? Data is transmitted over internet, but that's not all, right? So these systems are just for local closed loop automation, but in IoT we are doing much more. So we have explained a lot of it in the earlier lecture, but here we will also illustrate certain things. So IoT architecture is actually typically divided into 4 functional layers. The first layer is of course sensing and identification layer. That means it's the physical real world data that is being sensed or captured, and then we are also identifying what it is, right? Sometimes the data is very feeble, sometimes then we have to increase the value. Sometimes the data is with noise, so I have to clean the data. Once all this thing is done, then we identify what kind of data, what is the value of those particular data, what is the resolution, what is the actual range of that data, and so on. So it's the perception layer or the device layer. Now to do this particular kind of activities or within this layer, we require different kind of things. For example, we require sensors. Sensors are devices that detect physical parameters such as temperature, humidity, motion, air quality, pressure, and so on. Then RFID tags, radio frequency identification tags. It uses radio waves to identify and track tagged objects automatically. It could be a GPS system, global positioning system, which is a satellite-based system that provides real-world location coordinates. If I have this GPS chip inside my computer, it will lock onto the satellites, which is GPS or there are different satellite constellation systems, but GPS is the most common one, American system, and then there is Galileo, and there is GLONASS. So there are different systems are there. So all those systems those particular chips could with a antenna of course can connect with those satellites, and then it can show our exact location. Then there could be fully smart devices such as embedded system with sensing, processing, communication, all built in together. That means it is a system which can sense or can process as well as also communicate as well, right? Like a smart meter or a smart street light or a smart wearable, which all is part of IoT, right? So this is the first layer, that is the sensing and the identification layer. The next layer is the network construction layer. So already we have done a little bit about this. So this transmits data over devices to processing systems such as using communication networks. So we call this a communication or a transport layer, right? So what kind of communications? The first one is WPAN, wireless personal area network. It usually refers to short range communication involving Bluetooth, Zigbee. Zigbee is basically a short range wireless mesh communication protocol for low data rate IoT devices. So that means several of these Zigbee units are there, and it talks wirelessly amongst themselves, and they can communicate via that first they communicate between each other, and then it can send the information up to the server and all. Then there is wireless local area network. So this is basically nothing but the Wi-Fi. We all use it every day, and this is for medium range local connectivity, right? Then there is WMAN, which is wireless metropolitan area network, which is city scale communication using similar to Wi-Fi, which is also known as WiMAX. Then there is WWAN, that is wireless wide area network, which refers to long distance cellular communication using our SIM cards and mobile phones. So that use 4G, 5G, LTE communication. We all use that. The phone data transmission happens via that. Then there is LP1, that is again low power wide area network. So that means it's a wide area network, but it is very low power, so it's a new network this has come. Then there is of course the internet backbone, that is all this data travels all across the world, right? So global high capacity fiber network enabling worldwide data exchange also is part of this particular system. So then there is the information processing layer. So as we have discussed earlier, this is the middleware, cloud, or the intelligence layer, right? And this is where data is stored, processed, analyzed, and secured. So different components are there to it. There are data centers or cloud platforms. There are search engines. Data mining happens there as well. Then there is data mining, where we extract patterns and insights from large data sets using machine learning or some statistical analysis. Then there is security involved, like in encryption, authentication, privacy protection. That has to be also be part of this processing layer. Then smart decision system, like once we have processed the data, what to do, what would be the final decision. Like in case of adaptive traffic signal timing, we actually change the signal timing based on that decision, right? So all this is part of the information processing layer. Some happens in the device, some happens in the server, doesn't matter, but it is part of this information processing layer. So then comes the integrated application layer. That is, once the data processing is over, we are doing something like we are displaying the data somewhere and all. That means it is actually, that means we are delivering real world services based on processed IoT intelligence. So whatever data we are processing, that is now being delivered so that it will be used for meaningful ways. For example, in a smart grid, we monitor and optimize electricity distribution networks. In green buildings, we can monitor energy, or we can automate HVAC systems, lighting controls, and so on. And then in case of smart transportation, real-time traffic management can happen, fleet monitoring, dynamic routing, all these things can happen. Environmental monitoring means we can monitor air quality, water quality, noise level, all these things could be monitored and tracked. So that means once the IoT processes and it says that, well, it is processing the data, and then it can say that, well, it is high or low than the benchmark or from the baseline. So all this monitoring could be done via this integrated application layer. So looking into the different core IoT technologies, we start with the hardware, of course, the devices which are involved. That involves sensors, actuators, embedded boards or development platforms. So three parts: sensors, actuators, and embedded boards or development platforms, right? So embedded board means it's a circuit which has got a microcontroller and so many other things which helps to connect or sensors or send the information via serial port. It communicates via serial ports, and it could make some changes, like it could run a motor. All these things is part of this. Embedded boards are there to do that, right? Or development platforms, of course. So sensors, what they do is they sense the physical phenomena when they are occurring around them, and usually it is the real world is being observed by this computer or embedded system using these particular sensors. There is no other way. Or car which can drive autonomously is taking decisions at every moment, and that decision is based on what it sends around, right? So obviously we have to be very careful about how do I choose a sensor, what context we are choosing the sensor, and so on. Then actuators perform some actions on the physical environment, thus enabling the system to affect the physical world. So actuators perform some actions on the physical environment, thus enabling the system to affect the physical world. That means you are able to do something at which is changing the physical world. That means you can run a motor or you can move a vehicle. All this is actually doing something, actuation, right? So that means IoT system has some form of actuation. Now actuation may not be physically moving something, it could be displaying something on a screen. That is also actuation. And the embedded board or development platform is basically the programmable hardware system, or with the microcontroller and other which integrates a processor or a microcontroller, memory, then input output interfaces. That means what devices could be connected with it. Then this interfaces to control sensors, actuators, and communication in embedded or IoT applications. So that means all this communication, all these things happens controlled by the microcontroller, and this embedded system is the, you can say, the brain of this particular IoT device. Now, the second part is, of course, the technology is communication technology. We can use Wi-Fi, we can use Bluetooth, we can use Zigbee, we can use cellular networks, we can use LP1. All these systems could be utilized for communication. Then, what are the protocols for data transmission for IoT? There is MQTT protocol, which is very fast and very low bandwidth protocol. So then there is COAP, then HTTP, AMQP. So this all we have done earlier, and AMQP is a new one. This is Advanced Message Queuing Protocol, and most of these protocols are, except for HTTP, it is not that it doesn't have that much low power consumption, or it's not that lightweight, but still most IoT devices require protocols for low bandwidth, low power consumption, lightweight messaging and reliable data delivery, since these devices have limited power and memory and operate in unreliable network using wireless links, mostly wireless links, right? So that's why the protocols becomes important. So if, like MQTT we have already discussed earlier, it is basically it's sort of where you publish and then you subscribe, that in between there is a broker. So that actually reduces a lot of problems. That means it is a continuous stream of data being sent to the server, which is being recorded, and whoever wants to see it can see it, instead of direct communication with these two devices. So that actually improves the reliability of the system and so on, right? So that is why the protocols also determine which protocols are suitable for IoT devices and all. That also has to be thought of. Then there is the software ID, and that means there is the integrated development environment where I can write the software. Now this software is, could be written in Arduino. We have the Arduino ID where you can write the code, which is almost like C++. Then we can write code in Python or embedded C. So these are the different languages which we can use for programming that particular microcontroller. So ID is basically the development environment, of course, to write, compile, debug and upload firmware that enables microcontrollers and embedded devices to sense, process, communicate and control systems. So within the code we first specify which pin of the microcontroller, or rather you can say which arm of the microcontroller connects to which sensors, where is the power coming from, which things are connected together, all this, and then what will happen when there is some sort of a sensing, some sort of a information that comes into the microcontroller, like I sense there is fire, then what to do. So all this is written in the code, and that's the firmware, and this actually is developed or compiled, debugged, everything via the software ID. Then there is, of course, the cloud platform where we are uploading the data, and this is both for data storage, analytics, as well as for having dashboards as well. Now coming to IoT platform, you can see in the image that this is the Arduino platform, Arduino Uno platform. We will of course discuss this in much more detail later. So you can see that there are many things. So here there is a USB port, here there is a power port, there is the actual microcontroller over here, right? And then there is, then there are different, these components, like for example, there are certain components for power, related with power, certain components related with analog signals, that means it can receive analog signals. So these are known as pins. I can plug in some sensors into these pins, right? So Arduino Uno is basically this processor as well as the board with all these peripherals, right? So it is a combined system which could be used for doing, connecting sensors to it and then doing some actuation, right? So it's a microcontroller based development board, ideal for real-time sensor interfacing and embedded control applications, and this uses ATmega 328P as the microcontroller, right? And then, but this has got limited capability, and also the prices is also less. But now if I want to increase the capability, increase the amount of memory, or how much amount of code I can run in it, can I run more AI based programs in it, like connect a camera to this particular system, and then the camera receives the images, and this image could be processed within the code itself, right? So for that we require something with bigger memory, bigger bigger computing power and so on. So that is where Raspberry Pi comes in. So it's a Linux-based full single board computer. So it's a computer in its own, and it could be used for edge computing, networking, and also intelligent IoT applications. Then there is a BeagleBone Black platform. This is industrial grade embedded platform for automation, robotics, and smart grid control, used in industries and so on. And then there is ESP32, which is very, very common. It's a low cost Wi-Fi Bluetooth enabled microcontroller, widely used in modern IoT systems, and it supports MQTT, HTTP, web sockets, and can be used for different projects, which could be Industry 4.0 projects, wearables projects, mobility projects, smart city projects, and so on. So along with these platforms, which are available from the directly from different manufacturers, we also have semiconductors which are available, and the semiconductors are designed by different companies. I have given you two very popular ones, which is Nordic Semiconductors and the other is Quictel. So these are two companies which have a line of semiconductors or microcontrollers, microcontrollers, which actually would be used to design this kind of, around which we design the IoT device. So in case of Nordic, I have not given the image of it. We also use that in our lab for Bluetooth communications with bicycle smart locks and all. So we will see that later in some lecture. So it's a ultra low power wireless microcontroller widely used in battery powered IoT devices. So if you want to save the battery for a long time, right? So you use this kind of very low powered microcontroller, and this comes from Nordic, particularly the NRF 5382 series controller. So then there is another company, Quictel. They make industrial grade cellular IoT modules enabling LTE communication, NB IoT, and then it could also allow us GNSS connectivity for large scale deployment in fleet management, smart meters, vehicle tracking, and industrial telemetry. So under this Quictel, similarly, similar to Nordic, also has got many processors, microcontrollers under that. Similarly, Quictel also has got many processor series like EC series processor, BG series processor, EG series processor, M95 processors. Each series are specialized for certain things like GSM, M95 for GSM, EG series for LTE, then BG series is for NB-IoT or LTE-M, then EC series for 4G LTE category Cat1. So you see this Quictel MC60E is also a microcontroller. This also we use in our lab. This PCB is designed for one of our projects. It's a smart IoT device. So we are using this one is the Quictel controller which we have put in. Now in this case the PCB or the peripherals are designed by us only. That means here we have not used a board. We have bought the microcontroller, we have designed the circuit, like this microcontroller needs to be connected with accelerometer, it needs to be connected with a speaker, it needs to be able to be charged by a battery. All these things are done, right? So that means instead of a ready-made board, we are making our own PCB or printed circuit board, and we are putting all the components within it to do whatever we want. So this is a custom board with a microcontroller which is available from market, and each microcontroller has got certain capabilities. Accordingly we choose them. For example, here the microcontroller is EC200U-CN. So it is a 4G LTE Cat1 cellular module widely used for vehicle tracking. GNSS, GPS, GLONASS, both is actually you can track both constellations you can use, and urban IoT applications requiring wide area connectivity is actually we use this kind of devices, right? So both these devices are from work done in our lab, and we are preparing IoT devices which uses this kind of circuit boards and this kind of microcontrollers. So then coming to the software part or the ID part, there are different IDs depending on which microcontroller you use. You may have to use different IDs. For example, if I use Arduino board, then I will go for the Arduino ID, and we use it to write, compile, and upload programs to microcontrollers. First we write the program, compile it, see if it is all working fine. Then, of course, we test it in the code level itself, and then we upload it into the microcontroller using sometimes USB port. We can do that, or some serial ports are there. And then what we do is we see if the microcontroller is acting in the way it is supposed to. If it is fine, then the code is fine. Otherwise, we again debug the code and again upload it into the microcontroller. So we can do it again and again. So so this could be done in, we can use Arduino IDE for both Arduino as well as ESP32, and the syntax is almost like C++, not that difficult to learn, and also Arduino has got many built-in libraries, and each library is for different kinds of sensors, different kinds of actuators, different kinds of communication protocols, and based on the functions of those libraries and all, we can utilize the functions and those libraries to do whatever we want to do. So it is not like you can remember everything altogether, but as per your requirement, you will study or you will use the internet resources to find out which functions and how it has to be written. Accordingly, you can add them in your code. So Arduino allows very rapid prototyping, and communication happens via different channels. So we will again talk about those later in our, when we discuss Arduino in detail. And then embedded, instead of Arduino C, we can go for embedded C as well. It's a low-level programming language compared to what we were using in Arduino, but it is used for writing efficient hardware-oriented code directly for microcontrollers, and this allows precise control over memory, registers, timers, interrupts, peripherals, and so on. Now, interrupts are something where the microcontroller waits for some change, right? So that means as soon as the change is happening, then it wakes up or then it triggers certain kinds of activities. So that's an interrupt. For example, if I have a microcontroller, we are using the interrupt to detect that if the accelerometer is, that particular vehicle is moved, the accelerometer will record some changes, and that will raise that particular request or that interrupt to actually the microcontroller to do some process. Then there is the Python. Instead of embedded C, we can also go for Python. It could be MicroPython, Circuit Python, or Raspberry Pi Python. So different ways we can use Python here, and it could be used on both single board computers like Raspberry Pi or microcontrollers which supports MicroPython, of course, and allows fast development, easy debugging, and integration with networking, AI, and cloud platforms. All these things could be done, and mostly used for IoT gateways, data logging, and edge analytics, right? So that means I want to run some AI programs and all in a device, and that is where edge analytics, this kind of using MicroPython is very, very common. Then for firmware, that means all this code that we would be writing through this IDE, and that has to be stored in the microcontroller's flash memory. That means first we have to write the code, compile it, and debug it if required, and then again compile it. Further, when the code is stable, we upload that into the microcontroller's flash memory, and then the microcontroller uses that code to take actions, right? So based on whatever is written in the code, whatever needs to be done, microcontroller will do those things, provided there is some input going to it in form of a stimulus which actually some change is detected, and it can start running the code as per instruction. So this could be used to control the device hardware, and the compiled binary file from Arduino IDE after I've written the code and compiled it and so on, or using Arduino IDE or embedded C, it becomes the device's firmware. So the compiled code is the device's firmware. So firmware runs directly on the hardware and controls sensors, communication modules, actuators, and manage security, power management, and device control logic. So it is not just sensing, sending information, and so on. All the management of the device itself, like when to turn off power, when to go to sleep, and how to sense and everything is controlled via this device control logic. Everything is written is part of the firmware. So these are some of the references we have utilized. To conclude, modern IoT architecture extends classical computer process control by integrating sensing, networking, cloud intelligence, and embedded platforms to create scalable cyber physical systems. Thank you.